Now, back when I was working for my dad's trucking company as a teenager, whenever we'd unload a truck and get to the last box in the trailer, my dad would always say, "That's the one we were looking for." And I think we can say the same thing about this chapter. We've reached chapter 15, the last one of the semester, which has to do with solutions. So what exactly is a solution? Well, we talked about this back in chapter 4. And we said back then that a solution is simply a homogeneous mixture of two or more substances. So back then we defined homogeneous mixtures as solutions. Now we're simply doing the reverse, saying that a solution is a homogeneous mixture. All solutions contain two components. One of those is the solvent, and the other is the solute. The solvent is the thing that does the dissolving. It's the substance that the other materials dissolve into, and the solute is simply the materials that are being dissolved. You can only have one solvent in a particular solution, but you can have many solutes. Seawater, for example, water is the solvent, but there's oxygen and salt and calcium, magnesium, even some gold. There's a lot of different things dissolved into seawater. So how do we identify which substance is the solvent in a solution? And there's actually two different things we have to consider. First, if all the components of the solution are in the same physical state, either they're all gases, all liquids, or all solids, then we go by whichever one is the most abundant, so whichever one there's more of. Good example would be air. Air contains a number of different gases. Nitrogen is the most abundant of those gases, and therefore we would consider nitrogen to be the solvent in air. And the oxygen, the carbon dioxide, argon, etc., those are all solutes. If a solution contains only liquids, vodka is a good example. Alcoholic beverages are mostly alcohol and water. Vodka happens to be 40% alcohol, which means it's 60% water. They're both liquids, so we simply pick the one there's more of, and that means that water would be the solvent in vodka. On the other hand, if you're thinking of Everclear, Everclear is 95% alcohol and only 5% water. Again, they're both liquids, so the solvent is going to be whichever one there's more of, and in that case, that means alcohol is the solvent. Water is commonly the solvent in most solutions. The one exception is in a case like this, where you have water mixed with another liquid, and that liquid happens to be present in greater amount. The second thing we need to consider is what happens if the components are in different physical states. Say you have a solid and a liquid, or a liquid and a gas. In that case, we don't go by the amount. Instead, we look on the physical state of the solution. Honey, for example, is a solution that consists mainly of sugar and water. In honey, you have about 85% solid sugar and only 15% liquid water. So you might be thinking, I guess sugar must be the solvent, but that's not the case. Because they're two different physical states, we look at the physical state of the final solution. Honey is a liquid, and water is a liquid, and therefore water would have to be the solvent. Even though there's more sugar, if the water dissolved in the sugar, we would end up with a solid result. But if the sugar dissolves into the water, we end up with a liquid. The solvent in a solution can exist in three different physical states, gas, liquid, or solid, and the same is true of the solute. And that means there's 9 possible different combinations of solutions you can have with those different physical states. The first one, and one that we've talked about earlier, is a solid dissolved in a liquid. That's a very common kind of solution. Water tends to dissolve a lot of different things. Syrup is a good example of that. Syrup, like honey, is mainly a solution of sugar in water. You can also have a liquid dissolved in a liquid, and that's also one we talked about just a little bit ago. Our alcoholic beverages like the vodka or the Everclear, those are solutions of either alcohol dissolved in water in this case, or with the Everclear it was water dissolved in alcohol. A gas dissolved in a liquid, you might not be understanding what that might be, but it's actually something very common. All soft drinks are an example of a gas dissolved in a liquid. That gas is carbon dioxide. That's what makes carbonated beverages carbonated. They basically dissolve a lot of carbon dioxide into the water, which is the solvent in the soft drink. A gas dissolved in a gas, that's again one we talked about a little while ago when we talked about air. Okay, air is a mixture of gases, and since nitrogen is the most abundant of those gases, that means that in air, nitrogen would be the solvent. Now, a liquid dissolved in a solid, that's quite an unusual one. There aren't very many examples of that, but one common one is dental fillings. Those old-fashioned silver fillings that they tend to not use much anymore, but they were made of a solution of silver and mercury. Silver is a solid and mercury is a liquid, but dental fillings are solid. And that means that between the two, the solid silver must be the solvent and the liquid mercury must be the solute. So it's liquid mercury dissolved in solid silver. A solid dissolved in a solid, those are actually very common. Any alloy, any kind of metal alloy is an example of that. Bronze, that they make bronze medals out of for the Olympics or other sporting events, is an alloy of copper and tin. So copper is more abundant, so copper is the solvent, tin is the solute. 14-karat gold, which most jewelry is made out of. They don't make jewelry out of pure gold very often because it's very soft. It bends real easily. So 14-karat gold is about 60% gold, and it's got blended in some zinc and some silver and some copper. Stainless steel, like our silverware or stainless steel sinks, is a blend of iron and chromium. There's about 10% chromium mixed in with the iron, and it keeps the iron from rusting. Now, a gas dissolved in a solid, that's a rather unusual one. I only know of one example, and that is hydrogen gas actually will dissolve in palladium metal. It can just suck up huge amounts of hydrogen. The hydrogen molecules sort of tuck themselves in between those very large palladium atoms. So that's a very unusual example, only one that I'm familiar with. Now, there are two other possibilities. First would be a liquid dissolved in a gas. And it turns out that's not a possibility at all, because the only way you can dissolve something into a gas is it has to be converted into a gas first. So liquids don't just dissolve in gases unless their molecules first separate from each other. And of course, once their molecules separate, they're now gases anyway. So that one isn't a possibility. Same thing is true with a solid dissolved in a gas. You can't dissolve a solid in a gas without first breaking the solid apart, and if you break it apart, it's not a solid anymore. Now it's a gas. So of the 9 possibilities, there are 7 of those that are possible, and these 2 that are not. So why do solutions form in the first place? And it's the same reason that most chemical and physical changes occur, and that is because the atoms want to form stronger bonds. That is the driving force in chemistry. It's that desire to get the strongest bonds that something can get. So let's take a look at an example here of dissolving salt in water. So we have our sodium chloride crystal here. We have some pure water, and then we have our final solution. There's 3 steps that are involved in forming any solution. The first thing we have to do is to break the bonds in the solvent. The water molecules are attracted to each other, and we need to separate them to make room for the sodium ions and the chloride ions. So, as we learned earlier in the semester, breaking bonds always requires energy, which means this will be an endothermic process. It's going to cost us energy. The second step is to break the solute bonds. So we need to separate the sodium and chloride ions from each other, and just as with the water, breaking those bonds is going to take energy, which means it's also going to be an endothermic process. So at this point, things aren't looking real good, because we know that salt spontaneously dissolves in water, and we learned back in Chapter 7 that all spontaneous processes have to be exothermic, yet so far it's completely endothermic. So let's look at the third step. In the third step, we're going to form bonds between the water molecules and the sodium and chloride ions. And if breaking bonds requires energy, then forming bonds must produce energy, and therefore this third step will have to be exothermic. To find out what the overall process is, we simply add each of the steps together, and our overall energy change should be exothermic if this occurs spontaneously. It looks like it's going to end up endothermic. You're probably thinking, ooh, 2 endos probably beats an exo. Well, that is not true. As long as the exothermic step is larger than the 2 endothermic steps, the overall process will be exothermic. And that's what we would expect. We know the salt dissolves spontaneously in water. We know that all spontaneous processes are exothermic, and therefore the overall process in this case should be exothermic, and it is. Let's take a look at a couple of other examples here. Calcium chloride, similar to sodium chloride. If we take calcium chloride and we dissolve it in water, we know calcium chloride is soluble in water because the 95% rule tells us that. So calcium chloride is clearly going to dissolve spontaneously in water, and that means that that process ought to be exothermic. And if you put a thermometer in there, lo and behold, you will see the temperature rise, and that's exactly what we would predict. A spontaneous process, exothermic, causing an increase in temperature. But like any good scientist, we like to have more than one result to confirm our hypothesis, so let's do a second one here. This time we'll use ammonium chloride. So we'll take ammonium chloride and combine it with water, and again ammonium chloride should be very soluble in water, given that each ion has a charge of 1, and we would expect that to be a nicely exothermic process, but holy cow, it's not. It actually got colder. So what the heck is going on? Well, it turns out that there's something else at play here other than just energy. If you remember very carefully back to Chapter 7, when I gave you my rule about spontaneous processes, I said that all spontaneous processes are exothermic until Chapter 15. And guess what? We're in Chapter 15. So on our next video, we're going to talk about this other factor, which is known as entropy, that also has an impact on whether processes will occur spontaneously or not.